Alright everyone, it's Mr. Robs here, and today we're going to talk about theoretical probability and geometric probability. And so, just to recap, we have different kinds of probability. We have experimental probability, and that's when you actually do an experiment numerous times, and you look at the number of times the successful outcomes over the total number of trials. So, a scenario might be, if you would come along and you had a bin, big giant bin with all kinds of different colors in this bin of different beads, let's say. And if you came along here and you randomly chose a bead and counted, if we're looking for the probability of black beads, if we had lots and lots and lots of beads in here, if we randomly chose one, counted it, put it back in, randomize them again, grab the new one, counted it, put it back in, randomize it, counted it, put a new one back in, we would eventually find out whichever one, the number of successful black beads over the total number of times we would try it. Okay, and so that's experimental probability. We did this with the dice game the other day. Theoretical probability, though, is when we look at the number of successful outcomes over the total number of possible outcomes. And so if we go back to this idea of this bin, so if we were going to do this, the theoretical probability would be if we counted all of the black beads, that would be on the top, that would be success on the top, over all of the total number of beans, and that would be on the bottom of our fraction. And so that would be the theoretical probability. And that's the difference between the two. If we do the experimental probability an infinite amount of times, it equals the theoretical probability. Okay, and so if we just do this a large number of times, it's a pretty close estimate to the theoretical probability. All right, so here's example 1. If we consider a random event of tossing a coin, and I know then I could have a heads or I could have a tail. If John tossed the coin 50 times and he notes the coin landed heads 24 times, what's the experimental probability of getting a heads? Well, the probability of getting a heads then will be 24 out of 50. What is the theoretical probability of tossing a coin and getting a head? Well, the probability of coins getting a head, well, I know there are two possible sides and there's two outcomes, so it's 1 out of 2. Now, these two values are not the same, but they're very close. And the difference between A and B is that A is a very good estimate. That is what A is. And B is the theoretical outcome. Okay? I know that if I would flip the coin maybe 500 times, it would be close. If I did it 500 times, it would be close to 250. That would be the theoretical outcome. The experimental, I would expect it to maybe be 250 or 251, but close to 250. So the experimental outcome probability is just a very good estimate of the theoretical probability. The reason why it's important is because sometimes the only way to get the probability is via experimentation. Sometimes you can't do it any other way. So then, here we have a graph, and I want to know, what does this graph mean? Well, here are some of the points of this graph. Let A be the event that can be observed as either occurring or not occurring when an experiment is performed. So let's say my event is going to be tossing a coin. So I know it could be either heads or tails. Okay? And then I'm going to repeat the experiment n times, identically, count the number of times that A occurs. So maybe A will be getting ahead. Getting ahead. Okay, and so I count the number of times, this is the number of times I get ahead, NA. And then big N refers to the total number of experiments, total experiments taken out. And so this number, big N, is always larger than this value here. So then the ratio is the relative frequency of the event. So it is how often it happens. And by definition, this value has to be, this means between 0 and 1, or equal to either one. Because what could happen is if I toss it one time, okay, so if I toss my coin, let's say I toss it one time, and I get a head. Well, that would mean big N would be 1, and the number of successes is also 1, which is equal to 1. However, if I'm looking for the number of heads and I get a tail the first time, well, that's 0 over 1, which is 0. Those are the smallest values. And as you do more trials, it'll end up being either between these values. And so the experimental probability will tend, as you do it more and more, it starts to get toward the actual value of the theoretical probability as we repeat the experiment more and more times. And that's the key to experimental probability. You want to do it lots of times to get it to be closer and closer to the theoretical probability. Okay, let's try another example here. We have 2 cards to choose from the following pack, 2 A's, 3 B's, and a C. You replace the first card, and that's a key word, before choosing the second. So it wants us to illustrate it by doing the chart here. So you should pause the video and try and fill in the chart for yourself. Go ahead, pause it. I'm going to pause it too, and then it'll come back filled. So here's the chart all taken care of for me. Okay, and so now if we look at the probability of getting 2 A's, this is probably getting an A and an A. And this notation will become apparent later on, but this is 2 A's. So if I look here, I need 2 A's, and I can find that here in my table. And so I know there are 4 successes over a total of 1, 2, 3, 4, 5, 6 by 6 out of 36 in total, and so that's 1 out of 9. So then we could what's the probability of getting a B and a C? The probability of a B and a C. Okay, a B and a C. Well, if I want a B and a C, that's going to be B's and C's are, here are B's and C's here. Here are B's and C's here. Okay, so there are here, there's going to be 6 out of 36, which is 1/6. And then the D part is, what's the probability of getting any 2 letters the same? Well, that's the probability of an A and an A, and the probability of a B and a B, and the probability of a C and a C. Okay, so I'm looking for all those possibilities. And so what I see is I get, here are 4 possibilities. Here, B are a bunch of B's, 9 double B's, and 1 C. So there is 4, 9, and 1 is 14 out of 36, which is 7 out of 18. It's probably of getting any 2 letters the same. And so when we list our sample space, we can use this idea to count how many there are. And this is theoretical probability. Okay, I didn't do an experiment and try it out. I actually just considered abstractly what the possibilities were and my odds or probability of getting them. All right, last example. We have 3 coins are tossed. List the outcomes of the sample space. Well, if I have my first coin, and my second coin, and my third coin, I could have a head or a tail, or a head or a tail. Okay, and so if I want to list the possibilities, well, in order to list them, I think the easiest way for me is going to be to make a tree diagram. So I'm going to go to the next page and do that. I'm going to make a tree diagram on the next page. And so here's my tree diagram. My first time I flipped the coin, I could get a head or a tail. The second time, I could get a head or a tail, and a head or a tail. That's the second coin, And then the third coin, I could get a head or a tail, a head or a tail, a head or a tail, and a head or a tail, and so on. This is each color represents the possible coin it could be. And then when I put it all together, I could get head, 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 tail, head, tail, head, head, tail, tail. And be careful of the order, because the order does matter, because it's a different scenario that may have happened. And then get a tail, head, and a tail, and a tail, tail, and a head, and a tail, tail, and a tail. So in total, there's 1, 2, 3, 4, 5, 6, 7, 8 possibilities in total. So now, if I continue on, I've listed the outcomes. If I consider the rest of the question, it says, what is the probability of getting 3 tails? Well, if I look at all my outcomes, my 3 tails only happens down here. And so the probability of getting a tail, tail, and a tail is equal to 1 out of a possibility of 8. And this is a theoretical probability. We didn't experiment it or try it, we just looked at the possibilities. The next one, what's the probability of getting 1 tail? Well, if I want 1 tail, let me highlight here. I'm going to highlight. And if I highlight here, I know I want 1 tail. Here is 1 tail. Here is 1 tail. And here is 1 tail. So in total, I get equal to 3 out of 8. Then I want to say the probability of getting 2 heads. Okay. Now, the probability of getting 2 heads, if I consider this, well, here's 2 heads. Here's 2 heads. Here is 2 heads. Okay. And I'm going to change the wording here, probably of getting exactly 2 heads. And it's the same as getting exactly 1 tail, which is going to be 3 out of 8. And finally, the probability of getting at least 1 tail. Now that's a different question, this one. I want at least 1 tail. At least 1 tail. Well, if I think about this, if I want at least 1 tail, let me highlight here in pink. Well, here's 1 tail. Here's 1 tail. Well, here's at least 1 tail. There's a tail. There's 2 tails, 2 tails, and 2 tails. So I now have 7 possibilities. It's all but the first one here. And so at least 1 tail is equal to 7 out of a possible 8. And this is, again, the theoretical probability.